and discharging using the DAV converter. Okay, Jayadev, so you can start.
Thank you, sir. Good afternoon, everyone. Myself, Jayadev. Basically, I'm here to demonstrate battery charging and discharging using DV converter. This session basically is a laboratory session. Here we will see in real time how we can charge a battery using DAB converter and discharge also, and we will verify the bidirectional power flow from a DAB converter. Before that, um, I like to explain something about the DAV converter, how it's work and how the power transfer from one terminal to other terminal, and the how it's work as a bidirectional converter. Uh, this is the basic structural diagram of DAV converter. Here in figure 1A, we can see eh, if you look into the DV converter closely, we can see two full bridge converter are connected or coupled with a high frequency transformer. High frequency transformer in both side. Uh, if you draw a one line diagram of this converter, we can find that in figure B you can see in high frequency transformer can be represented as a RL. Obviously, you are neglecting the uh, parallel branch. Then the primary voltage and secondary voltage means output from the bridge one means primary bridge one, and the output from the secondary bridge one can be connected through a inductive element. We can represent this converter as the as this line diagram, whatever is shown in the figure 1b. Here you can see how the bidirectional power flow can be possible with this converter. If you make a phase difference between these two, Vp and Vs, then only the power transfer can be possible, which is the main principle we are using in this converter. Uh, with this, we are using not N1 is to N2 is not equal to 1. Most of the case is not equal to 1. Because of that, there is some problem like back power flow or circulating current. We'll discuss it later, and I will show you how this back power flow and circulating current is working in real life also. And before that, I will tell you how the switching sequence is switching is done in this converter. Left side, that's this converter overall we can say this is our first leg, second leg, third and fourth. This consists of a four leg. We will observe in the DAV module that there will be four leg. Each leg consists of two IGBT, one topmost and the other is bottommost. And figures 2 show the switching sequence for the converter. We can say switch 1 and 4 can be switched for a uh, switched with a single pulse, and the uh, inverted one, a complementary one, is given to the S2 and S3, and a phase difference between the S1 and S5, which are belongs to two different bridges. We are maintaining a phase difference between the S1 and S5. Like some 5, we are considering here 30 degree of phase difference. With this phase difference, the power can be flow. It can be mathematically also proved from the equation 1. The more the phase difference between the two bridges, the more with the power. In this equation 1, we can see free, power is directly related to the phase difference between the two bridges. This converter is nowadays more popular because of it has some extremely advantages compared to the other than like it has high frequency transformer, means when the of frequency is very high, it has some advantages. I will discuss later also. And figures 3, you can see in the figure 3, we, we see the voltages and current through the transformer or leakage inductance. Most of the case, this leakage inductance is combined with the transformer only. And if the transformer not met proper leakage inductance, then we'll add a extra inductance as a leakage inductance in the real time. Otherwise, it is considered inside the this high frequency transformer. We'll observe this type of waveform. Some we can see in figure 3, the first one, primary side is uh, leading compared to the secondary side with some phase alpha. With this, we can see whatever be the power, we are able to transfer from the primary side to secondary side successfully. And the reverse case is shown in the second figure, where you can see the secondary side is leading uh, secondary. Oh, so yeah, there is a mismatch here, but here I want to say that secondary side is leading compared to the primary side. Then we can transfer the power in the reverse direction from secondary to primary. These are the some key feature the DAV can provide. Because of this, uh, nowadays the DAV converter is more popular than the other converter, and most of the area in the microgrid or like a battery charging in EV charging, like that, we are using DAV converter nowadays. It's provide high efficiency bidirectional power flow. Bidirectional power flow, I can show you how it is working with the phase shift. Simple power transform is very simple. Only you have to maintain the phase difference. If we are maintaining the positive phase difference between the primary and secondary, then power transfer from the primary secondary. If we maintain the negative phase difference between the primary and secondary bridges, then the power transfer from secondary to primary. And the how much power it will transfer, it depends on the phase only. The more the phase, the power will be more. Then ensuring safety and flexibility by providing isolation. As we using a high transformer, high frequency transformer between the two bridges and make it this converter. Because of that, the isolation, galvanic isolation is inherently provided with this. With this, the safety also come. And next point is can handle a wide range of input output voltage with high frequency. Why we are saying high wide range of input and output voltage? As we are using the transformer in between this, we can change the turn ratio. We can decide in a multiple turn ratio. You can also define you can set like a tapping we provide, and multiple turn ratio we can give. Because of that, we can go from a very wide range of input output voltage. Here in our experiment setup, we are using from 40 volt to 300 volt. Okay, then coming to the next point, it can able to eliminate the switching losses, as this converter is designed for the high frequency. Like it can, in real time, even if 100 kilohertz, it working on 100 kilohertz frequency also. At this high frequency, it eliminates the switching losses. How this eliminates switching losses? By providing soft switching concept by like ZVS and ZCS. Because of that, the switching losses is uh, less, or we cannot say fully eliminate. We must minimize, just minimize to the very low value. Then high power density, compact design with high frequency. Why we say compact design? As the frequency, see, if a converter size is mainly defined by the transformer size, heat sink, and the filter also a transformer, we can say. Because of this component, the converter size is increase only. If you uh, the transformer size, how it depends on the transformer size. If the frequency increases, we see in the transformer voltage is diagonally proportional to the flux and frequency. If we increase the frequency to a very high value, for a particular voltage, the flux requirement is very low. At that uh, low flux means that path, reluctance path requirement is very low. Hence, we can say the core area and the winding also very low. Means only small transformer can be used for the particular voltage uh, and very high frequency. And the heat sink, as this converters provide soft switching, we can eliminate the switching loss. Man, at high frequency, our main problem is the only switching losses. If you are able to eliminate the switching losses, then that converter is very efficient. That's why we're saying very efficient converter. If you are able to eliminate the switching losses, it means the heat sink requirement in the converter also very, very small. Very small. Overall, the converter is became very compact. Even though the converter is 1 2 kilowatt, the overall converter size will be very less. These are some simulation result. I have taken inductance value at leakage inductance 200 millihenry at 20 kilohertz. And the primary side, I am using a battery having 48 terminal voltage, and output side is connected to the DC link, which is having 220 volt. With this, we will get this type of waveform. The primary is around, you can see in the figure 4, the primary voltage around 48, 50, because this is nominal voltage is coming from the uh, battery. That's why it's showing some 1 2 volt extra. And the output side, you can see is it's 220. With this, the leakage inductance current will be of this shape. We'll observe in the real time also. And the figure 5 shows the charging of the battery. When we make phase difference is negative between the primary and secondary. This charging waveform will get the SOC level. First section of figure 5 shows the SOC percentage. We can see it's increasing from 50% to, oh, from 50% it is increasing with the charging current of around minus two ampere. I have considered the charging. I have considered the battery current, discharging battery current is positive, so that's why it's showing the negative. Uh, Negative currents mean battery charging, and the voltage is maintained at 48. Similarly, in the figure 6, we can see for the discharging case, SOC also showing the its SOC level is decreasing from 50 to from 50, and the battery current is 2 amperes, a positive, and the remaining nominal voltage for the battery is remain same. An experiment, already we have checked this experiment or verified also. From 6 figure C, we are for the charging and discharging of this battery using a DAB converter, we are using SPS modulation switching technique. That is single phase shift modulation technique. There are more than one modulation technique, several modulation techniques like um, EPS, DPS, TPS also, but you are using only simple one. Simple one. Those have many advantages. Like EPS, I already told some back power and circulating current will be there with this switching sequence. That will be eliminated with EPS switching, EPS modulation. But we are using here only SPS. We are giving a 30% of phase shift from the C2000 microcontroller to the IGBT. Then we will observe figure 7, the voltages across the transformer and the current through the leakage inductance. And H we are using a transformer having a turn ratio 300 is to 40. That's why with 90 volt we'll get around 30 volt only with this turn ratio. That's why this figure 8 shows the charging of the battery. Why it is 13 volt? Because we will kept intentionally the nominal voltage at the battery side more than the 12 volt, and this can be done to charge, and the phase shift will be advanced from the secondary to primary, while secondary is connected to the source and primary is connected to the battery. And while charging the battery, one should kept in mind that the battery can be charged up to a current which is less than the 25% of the battery capacity. This should be remain. This should be careful while charging the battery. Okay, then figure 9 shows the discharging of battery. We are giving a of we are giving 12.1 volt from the battery, which is the terminal voltage of the battery, and we connect a uh, resistive load in the output side, and we'll measure the voltage and current, how it's coming, and all the waveform will be shown in the DSO. For this experiment, we are giving using a frequency of 20 kilohertz, and the battery of size having 42 ampere hour capacity, having 12 volt amps output voltage, and the inductance with the capacity with the high frequency transformer. The high frequency transformer, the leakage inductance is combined with this, which is having a 14 millihenry, and will give around 90 volt in the from the source through a variac then a rectifier. I'll show all this thing, and we'll keep the output voltage at 12 13 more than 12 13 volt, and we'll see the charging current in the battery. This is the setup. We'll see uh, here. We'll see C2000 microcontroller. The code is down in the C2000 microcontroller. Will provide four 4 PWM signal for each leg. For first bridge, primary bridge, two signal, and for secondary bridge, two signal. Or both signal will have phase shift of 30 degree. We'll see. This code is dumped in the C2000. From the C2000, the PWM is generated at 3.3 voltage level. We need to trigger the IGBT. We need around 15 volt, 15 volt PWM signal. To do that, we are using a phase shifter, 15 volt DC phase shifter, to shift this 2.3 volt into 15 volt. Then we are giving that PWM signal to this one, the get terminal of the IGBT. This is the battery we are using, 42 ampere hour capacity, 12 volt. This is the DAB module. We will see 1, 2, 3, and 4 legs. These two are for the primary legs or low voltage side leg, and these two are for the high voltage side leg. These two are connected through the transformer. You will see a side, a small transformer is there. This transformer having 14 ampere millihenry, its inductance value. We are connected through these two bridges are connected through this transformer. Then in the output side, we will use for discharging purpose one resistive load, and charging purpose you will use a variable transformer, auto transformer, and from there the AC will come. From AC to we will use a rectifier, small rectifier that will rectify, and then we will give the uh, rectifier output to secondary or bridge terminal. Okay, let's go to the experimental setup, and uh, we'll do experiment how charging, and we'll measure charging and discharging current also. Just to wait 2 minutes. I'll be live on experimental setup. I think video is available. Am I audible, sir?
Yes, sir.
Okay. This is the DAV converter. This is the battery, 42 ampere hour battery. This is DAV converter. This is microcontroller, C2000 microcontroller. From this microcontroller, you are using a IGBT driver circuit. You are giving 2.2 volt. Then using the level shifter, will shift that voltage to a 15 volt. Here you see, here come here. Here you'll see four. 1, 2, 3, 4. 4 lags. Each lag having two IGBT switch from top and bottom. And here all the terminal are given. Here terminal here. First one ground. Third is for the topmost, and four is the bottom. Like that, all the bridges is given. Terminal of the bridges is given. So we are giving a signal to three. I have sorted here 3 to here 4, means S1 to S4. Like that, I have sorted. All the things are connected in here. We will check uh, first the phase difference between two bridges. Okay, it's making difficult to find. Holding it. Okay. Here we can see from the CRO, DSO, the phase difference between the primary and the secondary bridge is 30 degree. Here you see the secondary bridge is this one. Means yellow one is the secondary bridge, which I will connect a source that is leading. Yellow one is leading from the blue one. With this, that we can say the power is transferred from the secondary bridge to primary bridge. We'll turn on this one. This is the variac we are using to supply to charge the battery. From the variac, we are rectifying this AC signal to DC. From this DC, we are giving supply to the DAV converter. We'll see. This is the current probe, which will show the charging current or discharging current of the battery. Let me turn on the DAV module first. We'll check the voltage level here first, then we will change it. Means we required 13 volt at the output side. For that we are using a 300 is to 40 turn ratio transformer. That's for that we need around 98 volt to get a 13 volt in the output side, in battery side. We are making this 98 volt, then we'll connect this one to the DAB converter, then switch on the and see how the charging current is coming or not. Before 91. Okay. 107. Two. Around 98. Now we can integrate this one. I'll switch on this one. AV. If you see here, the charging current is coming. Current is coming negative. Here, this is the zero level. The current is coming negative. I said around 5 ampere means one one division is 5 ampere. If you say we will getting around charging current around 5 ampere. With this, we can say the battery is charging. Okay. Or if we check the voltage in the output side, battery side, this is only positive, negative, we'll get only 12.1 volt. If battery is here in the full functional phase, while it is discharge or charge, only few point 1 2 voltage will be difference. There is no difference between the terminal voltage. Only current will be changes. And we'll see that is charging current and see the inductor current. Okay, let's see. See the inductor current here, leakage current. See. The shape whatever I have seen shown in the figure in the simulation, the current is around the same. It is a experimental setup. That's why some deviation is there, but you can say it's perfect. Okay. With this, the charging process is completed. Switch off. Then we'll see the discharging process. For the discharging, we'll change the phase sequence. How will change the phase sequence? We just alternate this one, right? See, if I change the leading to lagging, this primary side I will change to lagging. Battery side will be leading this time, and the source side means uh, in the source side. Earlier we connect the variac, now we will connect a resistive load. See, earlier the yellow waveform was leading. Here we see the blue one is leading, means the battery side is leading now, and the source side means in in place of source we'll use a load, resistive load, to discharge the battery. Before that, I need to connect this source into the resistive load. If any residual energy stored somewhere, it will be discharged through this load. Okay, that's why I now this is the load terminal. These two are connected. See, this is the load box. We'll connect this into the primary into the secondary side. Earlier it was connected to the source. Now it will connect it to the load. We'll see how the current is flowing. Is on. Now I'll switch on this one. See, is the current. The current is positive. Positive means it's discharging current. Current is discharged from the earlier it was negative. This time it is positive current. It's around uh, 5 ampere. 5 ampere. Here it is said. Oh, it is said in around 10 ampere. 10 ampere. It's said around 10 ampere. This is okay. Now this one is completed. The discharging part is also completed, and we'll see the waveform of leakage inductance. See, leakage inductance. See the same. The same is maintained. Whatever I have shown in the simulation file or hardware also. This is maintained same. Now I'll show you something regarding the back power flow. Okay. If I remove, even if the load, there will be some current flowing through the battery. Let's see, observe. Oh, I need to turn off this one. I don't want to risk. Okay. I'll remove this load. And if I turn on this one, then also some current will flow. Connect here. See, till now, some current also flowing. One means 2 ampere, around 1 millihenry, 200 millihenry, its current is flowing. even if open at the open circuit. And it's providing some current. The current is circulating here. Circulating because of the circulating current, it will generate more heat. Will to reduce the circulating current, we'll use different modulation technique like EPS, DPS. Okay, with this, the hardware demonstration is over. I'll go to the simulation part. Uh, that PPT presentation, I will show you something the application how these are applicable. Now I will conclude. Coming to this application, uh, because of these advantages, we are using nowadays in renewables energy system like solar, wind for charging the battery and discharging. Energy storage, obviously confirmed from the experiment also. Microgrid distribution and the EV charging also. And with this, something with these advantages, there are some challenges also in this converter, like complex control technique for the phase modulation. This is whatever I have shown. That one is very simple one. But if you go to the EPS mode, EPS, TPS, DPS, then that those are very complex. Means you have to control around 8 switches to control 8 switches and eliminate the back power flow. That is very difficult, and you need a very complex algorithm also for the closed loop control. High frequency transformer design also very difficult. That leakage inductance value play very critical role on power transfer, because all the because of this the phase shift is coming. With the phase shift, power transfer is coming. Indirectly, you can say the inductance play a very crucial role in power transform from the primary to secondary bridge. To design that one at a particular value of power, uh, considering all the back power flow, turns ratio, all these things, it's a bit difficult also. And with this means I have shown at no load also some current is flowing also. If you put the take very light load, most of the power will be gone as a losses only. This is helpful only for mainly at the high power applications. At light load, the efficiency is very low. These are the some challenges we are getting here. With this, I want to conclude the DAV converter is very efficient at high power, and is uh, for battery charging and discharging. It is very efficient and versatile solution, and its bidirectional power flow capability combined with high frequency make it ideal for energy storage system and electric vehicle charging also. This is widely used in modern applications like renewable energy and EV because of its isolation and the efficiency, and soft switching technique make it very efficient converter regarding compared to other DC-DC converter. And these are the references I went through. Um, with this, I conclude my session. Thank you. If anyone having any query, you can ask.
Okay, thank you. If anyone having any query, please let us know.
Hello.
Yes, sir.
Yes, sir. This is Jeevan.
Okay.
So I want to ask two questions, sir. Like, I want to know how you calculate the value of inductance, like the leakage inductance. And the second question is like how you choose the phase shift. Like you have chosen phase shift of 30 degrees, right?
Yeah, yeah.
Yeah. So it is randomly taken or it depends on some parameter.
For a lab demonstration, I randomly take, not a purely random, how much battery can give the power, battery capacity, keeping in mind, and the load capacity. Both two are keeping in mind. I'm decide there will be a range, maximum and minimum value of phase shift.
Yes.
If you see the power relation, I'm showing this that equation one. You
Yes.
can see of uh, power is related to the phase shift, directly proportional to phase shift. So of considering the power value, input output power value, we can decide the phase shift value.
Yes.
And
Yes.
regarding the inductance value, there is a relation between the power, inductance, and phase shift. When that curve, one curve is there, it will looks like a
Increasing.
PV curve. PV increasing from the PV curve, we decide a particular value.
Yes.
At that
Yes.
value, we take the power and phase shift. With this power, the phase shift is related. Both two are related to each other. With this, we calculate the inductance value from this formula.
Okay. Okay. And that is like that is minus from the transformer leakage inductance, right?
Transformer leakage inductance.
You will use the external leakage inductance.
We whatever I have shown, that one is combined with the transformer.
Okay.
High transformer combined the leakage inductance, not to external to that. The leakage inductance is included inside the transformer.
Okay.
We are planning to separate that one.
Yes. So the value of L is the calculated value minus that leakage inductance of the ideal transformer, right?
Yes.
Yes.
And sometimes it's happened you calculate for the theoretical value the leakage inductance. That with that inductance, your simulation won't run. You have to manipulate. Means some increase, some few point increase or few decrease. You have to done like that only. Means this
Yes.
is the calculation value is very crucial here, because we are mainly depending on that curve. With that curve, we'll take some data and we'll put the power phase shift and they will calculate the L. That's why you have to, even if you call your simulation is running on that value, it doesn't guarantee that your experimental setup will work. You have to manipulate something, means you have to increase something, not like you are getting 200 millihenry or you are taking 200 microhenry or you are taking 1 millihenry, not that far. You have to,
Yes.
you are getting 200 means you have to go to 250, like 300, even if 150, like that you have to try.
Yes. Sure. Thank you for that.
Okay. Okay.
Okay. Is there any other query? I hope there is no query. Okay, so thank you, Jayadev, so for your
Thank
presentation and the demonstrations for your experimental setup. So today, now we are going to conclude day 3 session. Okay, so tomorrow morning again we'll start from 9 a.m.